Hi, this is the last video for chapter 10, Chem 2B, and it's going to be talking about the equilibrium constant paired with the Gibbs free energy and the Van't Hoff factor. So, similarly in Chem 2A, the equilibrium constant is still going to be the products over the reactants. And if you remember, the delta G, which is the Gibbs free energy, when it's less than 0, that means the reaction is spontaneous. And when it's greater than 0, when it's positive, the reaction is non-spontaneous. And then it's at equilibrium for both. When K equals to 1, the products and the reactants are at equilibrium, and the Gibbs free energy is also at equilibrium. So when the products are favored, that's when K is greater than 1, the reaction is spontaneous, and when the reactants are favored, which is when K is less than 1, the reaction is non-spontaneous. So this equation right here is the equation of the correlation between the products and the reactants with Q. And the first one here at the top is when the reaction is not at equilibrium. When it's not at equilibrium, you use the one at the top. And the second equation was derived from the first one, but when it's at equilibrium, so when delta G is equal to 0. So you use this one when you're at equilibrium. And I'm going to do a problem for that. For a problem like this, when you see, especially the key terms, partial pressures, and then they give you the actual partial pressure for the different substances in the reaction, your mind should immediately think, especially when it's asking for the, right here, it's asking for the Gibbs free energy, and it's in this form, where it has this degree thing at the end. When you look to this equation, you know it's going to use this type of equation where it involves the reaction quotient. And somewhere in the problem right here, it states that the reaction is at an equilibrium. So that means you're going to be using the second equation and not the first one, because the second one is when it's at equilibrium. And you'd remember this because it has a K, so it's different from that one. It has a K and the other one has a Q. So right here, to do this problem, first we have to find what K is. And as a refresher from Chem 2A, the equilibrium constant, it's always, in Chem, it's always the products over the reactants. But a key aspect of this is, in this situation, the moles matter as well. So the coefficient in front of each part of it, the H2 has 1, else has 1, and this one has 2. So why that makes a difference is when you try to find the equilibrium constant, you use the partial pressures of HI. Right here, it's this, and then you square it because it has a 2 in front of it. If it had a 3 in front of it, you'd cube it instead of square it. And then it's divided by the products on top divided by the reactants multiplied by each other. And if there were more reactants, you'd all multiply it by each other. And if there were more products, you'd multiply this by another one. And then you plug this into the calculator to find the K. This gives us an answer of 415.4 as the K. And now with that K value, we can finally solve this, where this is the equation. And how we do that is we just plug it in, since we know what the equation is and we know most values in the equation. The R, so there are two different R's that we've known throughout so far to this point in chemistry, where it's the 0.8206 and the 8.314. But they have different units, and the units usually depend, it usually determines what R you use. For this problem in particular, we're going to be using the 8.314 because it has the units of joules over moles times Kelvin. And the reason why is because when we find the delta G naught, which is this, it's different from this one. For this one, the units are just joules or kilojoules. But for this one, where it has the degree sign next to it, the units are joules over moles. You don't really have to memorize it because usually at the end, you get the, if you do things right, you get the right unit at the end anyways. And then back to this, if you multiply by the temperature right here, 700 Kelvin times the ln of the K we found earlier, which was 415.4. And you plug this all into the calculator, you get an answer of 35,088.9, the calculator says. So I'll just round it up to 35,089 joules over moles, because the Kelvin cancels out and the K doesn't have units, the K value. And that's the final answer. Or you can put it in kilojoules and have it be 3.5 kilojoules over mole. For this class as well, this is another equation that comes after you combine these two together, but it's not as important. You just have to know that it results in a straight line. But this is the more important equation that you guaranteed either in the final or the midterm, you're bound to have a question that involves using this equation. For the next problem though, we're not going to be using this Van't Hoff equation yet until the problem after that. But I'm going to show a new way that you can find this delta G naught through using the table instead of using this formula up here with the K value, this formula. I'm going to use a table of enthalpies and this one. Just like every other state functions, if you remember enthalpy and entropy, the Gibbs free energy with the not the it's different from this one. If you can remember, the Gibbs free energy also has the tabulated values, and you see the moles at the end. That means you have to multiply it by moles to get the kilojoules alone. And to calculate this, it's always the same thing. Like I keep saying in chemistry, it's always products minus reactants or products over reactants. So what you do here is you look at the equation here. It's 2 moles of HI, so it's 2 moles times whatever this value is, which is 1.7 kilojoules per mole, minus whatever the reactant is. But luckily for us, the reactants are substances in their, I forgot what they call it, substances in their natural state. So they have zeros. So we don't have to subtract anything, and we just multiply this, and it gives us 3.4 kilojoules, and the moles get canceled. So this value is the value for the delta G naught. And the question has, equilibrium, are the products or reactants favored? You can go back up here and remember that when it's spontaneous, that means the products are favored. And when it's non-spontaneous, that means the reactants are favored. And over here, the G value that we got is a positive value. So that means the reaction is non-spontaneous. And when the reaction is non-spontaneous, that means the reactants are going to be favored. So that answers the second part of the question. The reactants are going to be favored. And now for the third part of the question, we try to find delta G, not the delta G naught this time, but delta G. And before we learned that the delta G equation is equal to the change in enthalpy minus the temperature times the change in entropy. But throughout the entire question, we're not given any, we're given the enthalpy values. We could find the enthalpy of reaction, but we're not given the entropy. So we have to use a different equation. And if you remember, Not this equation though, because it doesn't have the, like I said, the delta G naught with this degree, it's different from just the delta G. So we have to go back to this original equation. Since we have this, we have that we just solved for the delta G naught, and R is a constant, and we have the temperature, and they give us pressure values to find the quotient. So since the reaction isn't at equilibrium, we can't use this one. We have to use this formula. So then we plug in this formula and try to answer the question. I'm going to rewrite the formula right here. The G naught is equal to, the G is equal to the delta G naught plus RT ln of Q. And to find Q, it's the same process to find K, which is the HI has 2 moles in front of it as a coefficient, so we square it once again. We do 2.5 square over the reactants multiplied to each other, 0.20 times 0.15, and we plug that into the calculator. When we plug that in, we get about 208 approximately as the Q value. And then now we put it back into the equation. The delta G is equal to 3.4 kilojoules plus, and remember the R is written in, the units are joules over moles times K. And right here we have kilojoules. So we have to use the same unit across each numbers. And for that we have to change, it's easier to change kilojoules to joules. So I'm going to change the 3.4 kilojoules to joules instead. So that becomes 3,400 joules plus 8.314 joules over moles times Kelvin. And we multiply this by the temperature given right here, 298 K times ln of the Q, the 208 that we just found. 208, and we plug into the calculator to find the final answer. And that's the answer for that. For the last problem, if we read through the problem, you can see there's a K value, and there another K value right here. And for these two K values, they give one of the K values here, but they ask you to calculate the other. So we know K1 is given, but we don't know K2. And there's also 2 temperatures given right here. So we know T1, which is given, and T2, they're both given. So usually when we see this kind of problem, we can already start thinking that it's going to be the Van't Hoff equation. And you're guaranteed to get a question like this on one of the tests. So these questions are usually not that hard, because as soon as you recognize it's a Van't Hoff equation problem, you just use the Van't Hoff equation, which is given to you in the equation sheet. And that equation goes, it's ln of K1. And also for this equation, the K's don't really matter. You're not supposed to put K1 on top or K2 on top, because no one told us that this value is K1. So you just pick whichever you want as K1 and whichever you want as K2. But the only thing that matters is the K1 and the T1 have to go together. There's a pattern to it. So you just pair the 2 K's, which is right here. You pair it as either K1 and T1 or K2 and T2. It doesn't really matter. And then you fill in the rest of the equation, which is ln of K2 equals to the delta H naught over R times 1 over. This is where the numbers start to matter. So if you put the 1 on the top, that means the 1 has to go, that means the first T has to be T2. minus 1 over T1. Or you can do it this way, where you put K2 on top instead. So that makes it easier for you. K2 over ln of K1 equals to this. So that puts T1 before T2. You just got to know the order, but you don't really have to memorize it because, like I said, it would be given to you. You just have to know which ones to pair together, which it should be usually next to each other. So you know these two are going to be paired, and then this one is going to be paired with something that's missing. So you can use either version of this equation. For the sake of this problem, I'm just going to use this one. So over here, I know what K1 is. K1 is 4.2 times 10 to the negative 3 over ln of K2. I don't know what K2 is. I know what the delta H naught is though. It's 58 kilojoules over, once again, for the R, we're going to be using 8.314. And because this unit, it's written in joules, we have to convert the 58 to joules. So we just multiply that by 1,000 and it becomes 58,000 joules over moles times K. Then we plug the rest in. T2, we know T2 is, we know T2 is 600 minus T1. T1 is written up here, which is paired with K1, is 850. And now this is where algebra comes in play when you do problems like this. So a log loop, if you've done calculus before, you know that logs can be, so ln of A over ln of B is the same thing as ln of A minus ln of B. So we can write it this way, where ln of K1, 4.2 times 10 to the negative 3 minus ln of K2 is equal to the same thing that's written up here. And since we're looking for ln of K2, we move this one to the other side, so it becomes negative ln of K2 equal to negative ln of K1, 4.2 times 10 to the negative 3. When you move it to the other side, plus everything else over here. 5800 joules over the rest, dot dot dot. So since I already know, I can all this, none of these are constants. So this is something that I can plug into the calculator. I'm going to plug it into the calculator and do it. When I plug all this to the calculator and subtract it by this, I get negative ln of K naught equals to 8.892. And then I'm going to multiply both sides by negative. Just gets rid of this negative and moves it over here. And then for another log property is if you raise a log to the e power, it gets rid of the log. So it becomes K2 equals to this plugged into the calculator, which is 1.37 times 10 to the negative 4. And that's your final answer. End of chapter 10. Last video on chapter 10.